Hello everyone, welcome to this session. We will now hear from Professor Li of the Institute of Theoretical Physics at Chinese Academy of Sciences, who will talk about dive inside the black hole, interior structure and dynamics. Please welcome.
Okay, thanks for the introduction, and thanks to organizer for inviting me to be here. So taking this opportunity, I would like to introduce our recent work about the internal structure of black holes. Okay, I'm from Institute of Theoretical Physics, Chinese Academy of Sciences. Okay, this work is based on many recent papers with my collaborators. There are many collaborators here. So Professor Ronggen Cai is from the same institute, and Professor Runqiu Yang from Tianjin University. There are many formal students and postdocs to be here. Okay, this is the outline. In the first part, I will give the basic background. So maybe some audience are not so familiar with the background. I will take some time to give you a basic introduction. In the second part and the third part, this is the main result of our work. And last, I will give you a short summary and a discussion. So since time is very limited, I will skip all details. But if you have any question, just interrupt me. I can give you more details. Okay. So as we know, black hole is the prediction by the general relativity. So what is a black hole? So black hole is a region of the space-time where the gravity is so strong that nothing, no particle or even the light can escape from it. So it has the boundary we call the event horizon. So the first black hole is given by Schwarzschild since the beginning of the last century. So the solution is very simple. It has only one parameter, the capital M, which is nothing but the mass of the black hole. And this is the spherical symmetry object. It's very simple. But you can see this solution contains the two fundamental features of the black hole. One is at r equals 2m. You see this component vanishes, which is nothing but the event horizon I just mentioned. Typically, people believe that this is the boundary of the black hole. And at r goes to 0, you can calculate the curvature of this solution. You find that the curvature of the space-time is divergent. So this is called the singularity of the space-time. Okay, if you are familiar with the Penrose diagram, so this is the space-time structure of this black hole. This is event horizon, and this is the singularity. Okay, so since last century, so we have known many important properties of classical black holes. So for example, Penrose and Hawking, they proved the so-called singularity theorems. It tells us that, so singularity I just mentioned, they are general phenomena in general relativity which occurs in gravitational collapse independent of the symmetry of the system. So I just mentioned in the last solution, so it has a spherical symmetry, but it does not matter. So it happens ubiquitous in general relativity. Okay, that's a very famous work by Penrose. And we also know the no-here theorem for black hole. So that means no matter which kind of black hole you have, it can completely described by three parameters, at most three parameters. One is the mass of the black hole, and the angular momentum if it rotates. And if you take a charge, like the charge of the black hole, that means given these three parameters, we can uniquely fix the black hole. Okay, so you can imagine, so if you want to describe a dog, how many degree freedom you want or we need. So the color, the size, or even the dog have different colors, it's white, yellow, so many or infinity degree freedom. But the black hole is very simple, although it's a very extreme object. So in this sense, black hole is the most simple objects in our universe. It's just highlighted by Chandrasekhar. Okay? And we also know 4 laws of the black hole mechanism. For example, people showed that the surface gravity of the black hole, of the stationary black hole, is a constant. Okay? For example, this is called the zeroth law. And for the second law, the capital A is the area of the black hole. That means the area of black hole will not decrease. So you can compare to the well-known laws of thermodynamics. You see they are very similar to each other. Okay, but this is just the classical black hole for classical features. So as we know, in classical regime, so the black hole has no temperature, no entropy. So it's just a very similar feature. But if we consider quantum effect, the story will change. Okay, using the quantum mechanism around the black hole background, the Hawking, he showed that black hole is a thermodynamic system. It can evaporation and even have the radiation called the Hawking radiation. So in that sense, they showed that the black hole can have finite temperature if we consider quantum effect. It also have finite entropy. You may still remember this very similar to each other, but if we consider quantum effect, they become the same, almost the same. Okay, actually, the entropy of the black hole is given by, is proportional to the area of the event horizon. Okay, and there are some important fundamental constants. So Kb is the Boltzmann constant, and C is the speed of light. H bar is the Planck constant, and capital G is the Newton's constant. You see, and you see the area law because it's not a volume law like a traditional thermodynamic system. Black hole has area law. Its thermodynamic entropy is given by its event horizon area divided by the total of Planck area. So this is the Planck constant, like this. Okay, you see there are many important fundamental constants in this. This is called the Bekenstein-Hawking law. So you see these constants are important in many different areas in physics. That means this black hole thermodynamics gives a very deep and a fundamental relationship between gravitation, thermodynamics, and quantum theory. But so far, how to unify general relativity and quantum mechanism is still one of the greatest challenges in our modern physics. We have no complete theory for quantum gravity. So although we know many features of black hole, but frankly speaking, what's the nature of black hole? We have no answer. Okay, but we believe that black hole is the window to the nature of the gravity. Okay, and in my topic, so I mainly focus on the internal structure of black hole. So that's because exploring the internal structure and the space-time singularities so are very interesting and fundamental topics. And it can provide a better understanding of black hole physics, gravitation, and even quantum physics. So why the internal structure of black hole are important? Let me give you some reasons. So the first is associated to the strong regime of the theory. So as I just mentioned, the general relativity is not the last story of the gravity. So you want to know what happens in the strong regime of the gravity, that may be a hint to the new theory of gravity, even for the quantum gravity. And we just mentioned the singularity seems a ubiquitous feature in general relativity. So if singularity, it maybe hint that the GR will break down near the singularity. Okay, if singularity do exist and can be observed, what will happen? Okay, and the last one we know, as a good theory, we want to make a prediction given the inertial condition, right? So that's called classical predictive, if a theory is a good theory. But if the singularity can form and can be observed, how to predict near the singularity? And if there, beside the singularity, if there is a inner Cauchy horizon inside the black hole, we can lose the prediction outside the Cauchy horizon. Okay, in that sense, the general relativity don't have real predictive power. So maybe you are not familiar with the Cauchy horizon. Let's give you an example. So this is a charged black hole called the rational Nordstrom black hole. So it's the solution. So it's a parallel diagram. This is the event horizon, and it has the inner Cauchy horizon here. So let's give you an inertial condition of the side of the black hole, like the red curve. You see, in this regime cannot be predicted by this inertial condition because this is the light. So light cannot be go there. So there are many important features closely related to the internal dynamics inside the black hole, like singularity theorem I just mentioned, or the cosmic censorship conjecture given by Penrose, and even the black hole information paradox, and even from the holographic duality side, like holographic complicity. I just mentioned, so there are many theoretical progress about the black hole, and indeed, black hole is the intersection of fundamental physics, astrophysics, and cosmology. So I just mentioned there are many breakthroughs. So there's famous scientists like since Einstein, the Schwarzschild, Carl Oppenheimer, and Chandrasekhar, and etc. But just black hole is a pure theoretical prediction. But more recently, due to the development of technology, so we not only listening the gravitational waves of the merging of two black holes, we also see the image of the black hole. This is the first image of black hole from M87 star. And although black hole we see in classical features have no radiation, have no light, but it can affect the orbit near the black hole. So from the proper motion of stars, we can see, or we will know there should be a massive object in this center. Okay, this is the orbit we see from our galaxy. And from this, we will know there is a very supermassive dark object in our galaxy. So according to our understanding, which is nothing but the black hole. So that means the black hole now has been confirmed by experimental and observations. So black hole is now a very real object. So as a real object, so it's nature to ask, what's the structure, eternal structure of this black hole? Like you have the apple, you want to know what's inside the apple, right? And indeed, as emphasized by David Haviland, who is the chair of the Nobel Committee for Physics in 2020, he just emphasized that the discovery of this Nobel Prize, okay, they have broken new ground in the study of compact and supermassive objects, just black holes. But these black holes still pose many questions that beg for the answers and motivate further research. So one question is the internal structure of the black hole. So okay, so this talk, we just try to show our result to understand the internal structure of the black hole. But I should emphasize that here we are only consider the classical regime. We don't consider quantum effect now. In some sense, we work in the framework of classical general relativity. Okay, let's give you the first example, the no inner horizon theorem. So I just mentioned, if there has the inner Cauchy horizon, this theory will lose its prediction. Okay, so let's consider this kind of theory. So it's the Einstein scalar Maxwell theory. So capital R is the rigid scalar, and psi is the complex scalar charged under the U1 gauge field. Okay, the charge is Q, and F is the field strength for the U1 gauge field. So we have the coupling, two couplings, capital Z, and the potential, capital V. So that depends on the scalar functions. So this is a very general theory for the Einstein scalar Maxwell setup. So let's consider the black hole in this coordinate system. So it's the black hole with high symmetry. That means its horizon can be spherical, planar, or hyperbolic. So here we have no constraints on this coupling Z and the potential V. So that in that sense, the topology of the black hole can be arbitrary because there is no energy condition we use. We don't need any condition. We just consider very general case. Z is the radial coordinate, and psi is the scalar here and has the electric charge. So this kind of black hole. And if we turn off the U1 gauge field, like this chair, so we can go to Einstein with a neutral scalar, and result also apply to this simple case. So let's just focus on the most general case. As I just mentioned, so we have no constraint on the choice of V and Z, so the space-time can be asymptotically flat ADS, the theta, or even other cases. So it's quite general. So we want to ask, for this kind of hairy black hole, does this black hole have the inner Cauchy horizon inside the event horizon? So that's our question. So if this is the equation of motion for this system, so suppose you can solve this equation analytically. You have the analytical solution. You can check it very easily, right? But you see, this is a very complicated nonlinear coupled equations. So we don't have analytical solution. So, but people can try to solve it numerically. You can find a numerical solution and check if there is any inner horizon. But you know, for numerical solution, you can choose some specific parameters. You cannot check all cases. And it also will take time. It's a very complicated system. So here we will give a proof. There should be no inner horizon. So the idea is given as follows. So suppose this is the event horizon. We have the inner Cauchy horizon inside the black hole. So that means the Blackney function f should go like this by definition, because it's definition for black hole. So it goes from positive to negative at the event horizon, and it will go so right or go so light or this way. That means the Blackney function f at both horizons, they are 0. But at the event horizon, f prime is negative in our coordinate system. This is by definition. And f prime at the inner horizon is not negative. It should go up to have a second horizon. And you can show to have a small solution, the gauge potential at both horizons should be 0. So this is the basic observation. And the next key feature is that, so we can find a radially conserved quantity we call the Q. Z is the radial coordinate, and Z goes to infinity is the singularity in our setup. Okay, you can show that this combination is independent of this radial coordinate. This can be proved by using the equations of motion. Okay, and this quantity depends on many fields like the metric, the matter field, the gauge potential, and have even this non-local integral. Okay, and it depends on the topology of the black hole, because k equals 1 is a spherical topology, k equals 0, this term is vanishing, it's for planar case, and for k equals minus 1 is a hyperbolic case. Okay, so since we have this nice quantity, it's independent of the radial coordinate. So let's evaluate this quantity at both horizons. And we know at this both horizon, f equals 0, at equals 0, right? So we have this very simple case like this. We can simplify this quantity, and we have this one. Okay, let's look this one carefully. So in the right-hand side, as we know this feature, that means this combination should be negative, correct? Okay, but this side, you see, for k equals 1 or equals 0, this one cannot be negative. That means in the non-hyperbolic case, I mean for k equals 0, the planar, and k equals 1, the spherical case, there should be no inner horizon. So in this case, you can show there should be no inner horizon for both spherical and planar black hole with non-trivial scalar hair. So this is the general idea. But for the hyperbolic case, you see both sides, because it's -1, are negative. So cannot exclude the possibility that there should be there has inner horizons. But we can prove that there only exists at the most one inner horizon in this case. But we cannot exclude all inner horizons. And indeed, we tried to find an example for the hyperbolic case that give you one inner horizon. And we indeed find this case. This for the what is a very simple potential. It's the minimal model for the free charged scalar. And we say the coupling z equals 1. It's a very simple case. And from our numerics, we can show that, you see, let's see it more clearly. So capital F is the yellow curve. You see, this is the event horizon. And it goes to 0 at this point. This is the inner Cauchy horizon. You see here? And meanwhile, you see the get potential AT, this purple curve. Also, they are both vanishing at these two horizons. Okay, this is one example we can find. That means we show there exists at most one inner horizon, and we can indeed find a numerical example. Okay, actually, this argument can be generalized to many different other cases. And for example, people find using this argument to show other no inner horizon theorems, like in Hordensky theory, in Gauss-Bonnet theory. And it also can be extended to the black hole with nonlinear electrodynamics. Okay. Actually, nonlinear electrodynamics has a long history in physics and has many motivations. As we know, if you know string theory, so Bohr-in field theory is a low end limit from string theory, and it's pointed by Bohr-in field in 1934. And even consider the loop correction for QED, you can also find some kind of nonlinear electrodynamics. It can also be used to construct a regular black hole, or even in cosmology and holographic duality. So for example, we consider this kind of theory. So like here, S is this Maxwell combination. So it's arbitrary function. Okay, you can also follow our discussion to find this radially conserved quantity. But here, have non-trivial contribution. Ls is the derivative L prime with S. And you can also follow our discussion to show that there is no inner horizon for the spherical and the planar black hole with the scalar hair. And we also show that if you give more constraints, like the energy condition, so here we consider the non-energy condition. So which means that this consider null vector, and this energy momentum tensor, and this condition is satisfied. This is called a non-energy condition. We can show that there is no any inner horizon even for hyperbolic case. So the argument is as follows. So using the Maxwell equation, you can have this combination. This prime is with the derivative with the radial coordinate, and you can use some combination. You see this quantity, and the K0 is the null vector. So if the non-energy condition is satisfied, so this quantity should be positive. That means this combination will be a monotonic increasing function with respect to the z coordinate. But and we just show to have a smooth horizon, the gate potential should be vanishing at both horizons. So this is not impossible. So in this way, we can exclude all inner horizons, no matter the topology of the black hole. So the cause is that we introduce a null-energy condition. Actually, we can also consider the more complicated case. So we consider the black hole with a charged vector here. So because for the vector here, for example, like this theory, the rho mu is the vector field charged under the U1 gate field. Because the vector have the spatial direction, right? So it can break the isotropy of the system. For example, consider this case. This vector has a condensation along the x direction, one of the spatial directions. Okay, so you see the system is become anisotropic. So x component and other spatial component are not equivalent to each other. So this is the anisotropic case. But it's homogeneous. Okay. Following our construction, you can also find that it regularly conserve the charge. So this charge is even simple than the scalar case. Okay, it only depends on this combination, and the gate potential is independent of the vector here. So we find a very convenient way to construct this quantity is following the North's theorem. So the idea is like that. You have the answers here, and then you have the effective action. Just put this answer into the action, and you can observe that this effective action has this scaling symmetry. So then following the discussion, like North theory, you can find this conserved charge. But as I just mentioned, for the non-planar case, this argument will not hold because there is no such scaling symmetry. That's why in the scalar case, you see for the non-planar case, this conserved charge has some non-local term. Okay. Then you can evaluate this quantity at both horizons. You can find this side is negative and this side is not negative. So in this sense, the inner horizon is not positive. Okay, so far I just give you many examples of some very general case. This example is in some sense very general, but we can ask more. So without giving a specific Lagrangian, can we constrain the internal structure of the black hole? Okay, the answer is yes. So here let's begin with the Einstein equation. This Einstein tensor is the stress tensor for matter field. So just following the parallels. So we should impose some constraint on this matter contribution. Yeah, because in classical level, okay, matter should satisfy some, we call it some constraints. So in textbook, we call the energy condition. So which will crucially describe the property common to all states of matter that are well established in physics. But they are sufficiently strong to rule out many unphysical solutions of the Einstein equation. Actually, energy condition is well used in gravity and in general relativity. For example, the original singularity theorem of Penrose and Hawking, they consider the non-energy condition and the strong energy condition, respectively. So maybe you are not familiar with energy conditions. So let's briefly introduce some very important energy conditions in general relativity. Okay, the first one we call the dominant. From this part is a non-energy condition I just mentioned. This is for any null vector. This combination should be positive or equal 0. And the weaker condition is given for the time-like vector. So this combination should be non-negative. And the dominant energy condition, it should satisfy the weaker energy condition and have this further constraint. That means this current is further directed, is non-space-like. And this one is called a strong energy condition. This combination should be non-negative. So it looks complicated, but its physical picture is very simple. For example, for this strong and non-energy condition I just mentioned, that means matter is just attractive under gravity. That's very natural, right? Because we know gravity is the attractive force. Okay, that's just this fact in general relativity. And this weak energy condition just means energy is not negative. Okay, and this one means energy flux is not superluminal. Okay, its physical picture is very, very clear and simple. Okay, then using the strong and non-energy condition, we can prove the general result for the static black hole. Cool. This is the main result. Okay, let's introduce this result to you. So let's denote gamma to be the cross section of the black hole event horizon, and the mu to be the Killing vector, because we consider static black hole. It has a time-like Killing vector. Okay, we can prove the following result. So first, if the Einstein equation and the following three conditions are satisfied, and we can show that there is at most one inner Killing horizon or Cauchy horizon inside the black hole. So there are three cases. The first case is gamma is compact like a spherical symmetry, or like a spherical or compact. We don't need any spherical symmetry, just if gamma is compact and the strong energy condition is satisfied inside the black hole. Okay, and the second one, if gamma is non-compact like a planar or hyperbolic, and has a hyperbolic or planar symmetry, and the non-energy condition is satisfied inside the black hole. And the third one is seems more complicated, because the gamma is non-compact and a two-dimensional surface, and its average scalar curvature is non-positive, and the non-energy condition is satisfied. With these cases, we can show there at most one inner horizon inside the black hole. Okay, since I have no time, I can show you the basic idea for the first one. The first one, in some sense, is easy to understand. So how to prove this? Okay, here, let's assume behind this is the event horizon. So the Killing vector, the norm is negative. If besides this event horizon, there are two inner horizons. So these two inner horizons. Okay, so the structure is like this schematically. And in this, we have this gray regime. Okay, at the boundary, Xc by definition should be vanishing. And since it is a static space-time, we can use the decomposition, 3+1 decomposition. So the metric in general can be given by this form. Okay, n is the function, and HAB is the space metric in this called sigma t, is a special curve. Okay, then the Einstein equation can also have these two parts. Okay, RD is the ridge curvature for this space-like surface, and rho hat is nothing but the energy density of the matter field. Okay, and RAB is the ridge tensor in this red curve, this space-like term, and the capital D is the covariant derivative on this surface. Okay, it has this combination. Okay, T hat AB is the space component for the momentum tensor. Okay, this one, since they are space-like surface, so this one is positive, right? Because no time direction. Okay, and this one, you can use some combination, you find this combination. Okay, which is nothing but the strong energy condition, like this. So that means if the strong energy condition is satisfied in this regime, we use the capital V, this gray regime. So this term should be non-negative. The capital D is the covariant for the space a space like the surface. Okay, so then from mathematics we know there is a maximum principle. That means the maximum of n square must be bounded of the surface of the boundary of sigma t. That means this is the two boundary. But by definition, we know if this space-time have two boundaries, two inner horizons, n square here is just 0. That means n square should be 0. It's not possible because we want the black hole with two inner horizons. But in this case, we show the n square should be 0. So that means they are in contrast to the fact that Casimir is time-like. So in this way, we excluded that the existence of the second inner horizon. Okay, that's the main result of the first case. So other two cases is more technically involved, so I have no time to show that, but you can see more details from our paper. Okay. Okay, now we just show that there is, in some cases, there is no inner horizon inside the black hole. So next, we want to know any more details of the interior dynamics inside the black hole. Actually, this is very interesting and challenging because inside the black hole, the nonlinear effect is very important, and the behavior is sensitive to the details of the model. So let's show you a very simple case of chart the free scalar case. This is a very simple case. And this is the event horizon, and this is towards the singularity. You see, when you after inside the event horizon, they can find very complicated behaviors, even for a very simple theory of free charged scalar. You see the oscillation, the orange curve is for the scalar field, has some oscillation. And meanwhile, the TD component of the metric will collapse exponentially. And then they can go through some very step area they call the Kastner universe. I will explain later. But here, we want to show some generic features for the geometry near the singularity. So there are very famous results for the singularity. They call the BKL singularity. Okay, they consider the dynamical evolution of the universe near the singularity. Okay, they found that BKL showed that it is described by the anisotropic chaotic solution of the Einstein equation. So you see this tau t is the proper time near the singularity. So this is the special part of the metric. This is the time part, you see. And this component P1, P2, P3, they satisfy this kind of condition. They call the Kastner condition. Okay, you can see that for the vacuum Einstein equation, at least one of the solution, one of the value is negative. So that means one direction will be shrink and other will expand. And this component will change chaotically. So it's very complicated behavior, even for the vacuum Einstein equation. So here we show that when the kinetic term of the scalar field dominate the system, that means we can ignore the contribution from the potential. The solution can be found like this. Okay, the scalar field is logarithmic, but other fields are power laws. And z goes to infinity, goes to the singularity. And also this singularity have the finite electric charge, like this. And if we introduce the proper time, so the solution has a very simple form, like this. Okay, the component pt, ps, and p psi is given by, depends on the space-time dimensions, and one parameter called alpha. Okay, and they satisfy this condition, which is nothing but the generalized Kastner form, the Kastner universe. Okay, I just mentioned we neglect the contribution of the potential, so this have this condition. Actually, this condition is very, very general. It allows the potential capital V to be arbitrary algebraic function, like a polynomial function, like this. Okay, So here, let me show you some numerical examples. Like for convenience, we introduce this combination, okay? For Kastner universe, this three combination will go to a constant near the singularity using these conditions. Okay, here we show you this case, a free scalar or even a complicated case. You see this event horizon. After event horizon, they are complicated behavior, but when you go to the singularity, this both all quantities go to a constant, giving you a stable Kastner universe. Okay, but we can cook some potential that can break this condition. For example, we consider an exponential form, like this can become the central term. And we can derive the analytically that around this value, this location, okay, this condition will be break down. So it gives you something, a power law, that ZC depends on the D and the alpha, okay? And we can also check this quantity numerically. Here we consider a central term with a very simple parameter, very simple value for gamma is, let's say, is 0.01. You see there we have the Kastner universe, and then it interrupts to another one. So we can read off this value we call the ZC. And if we have a very large value for gamma, it has a very complete oscillation. And we can put the ZC as a function of 1 over gamma here. Because gamma is equal to 0, is equal to infinity, you see. And the cycle are from the numerical solution we read from this point. And the red curve is the fitting function from our prediction. You see they agree with each other very well. That means no matter how small the parameter gamma, I mean we turn on this term, there should be a deviation from a stable Kastner universe. This can be also found from other kind of setup. Okay. And indeed, you see they are very complicated and interesting behaviors for this oscillation case. And indeed, this kind of solution has also been observed by other authors in different models. So how to understand this feature is still an open question. Okay, so far, I just show there are interesting internal dynamics we found in some specific models. We solved the equations numerically. And at the interior times, I just show a common feature is the emergence of the Kastner universe when we go to the singularity. Okay, and depending on the interactions, we can also show some complicated phenomena. That means we have the bonds between different Kastner epochs. Just here you see the very complex oscillation. Okay, so a natural question arises. Okay, can we classify the interior dynamics of hairy black holes? We all want to understand it more analytically, not from numerical solution. Okay, so the answer is yes, at least partially yes, based on our recent work. Okay, let's go back to the Einstein-Maxwell scalar theory. This is an even more general case. Depends on the coupling F, the potential V, and the coupling Z. This is the most general case for the Einstein-Maxwell scalar theory. And this is a hairy black hole, and this is the equation of motion. It's even more complicated. Okay? But we can show that if the potential term can be neglected inside the black hole or near the singularity, and this coupling function has this exponential form. This is very common from supergravity, superstring theory. We can have classify the possible behaviors near the singularity. So the first one we call the Kastner transition. So here I show the Z sign derivative. That means for the platform, that means a Kastner universe. So that means there are two Kastner universes. There is a transition at this point. And we can read off the component because in the Kastner universe, the psi as a logarithmic term with the component alpha. So we can read alpha from our numerics and the alpha here. In this case, you can show the sum of these two components have the fixed value, a unique value. It depends on space-time and the coupling kappa. The second one is we still have two Cartesian universe, some alternation between them. And in this case, the alpha before the alternation and after the alternation, they times each other is given by this one. Alpha times alpha I mean the next Cartesian universe is given by this value. It only depends on the space-time dimension. This we call the Cartesian inversion. Okay, how to understand this behavior? So the idea or the discussion is as follows. So for the Cartesian transition, we find that after complicated analysis, you see the equation of motion for the scalar is controlled by this quantity under some conditions. Okay, and this condition can be solved analytically. So using the constant variant method, if you are very smart, you can solve it. So we consider this kind of answers, and you can find this equation can be written as this one. This alpha tilde is a derivative with respect to the radial coordinate. And this one, you can find this analytical solution. It's like a tangent term. That means when z over zt is the transition regime, it goes to alpha goes to a constant, almost a constant. This gives you a Cartesian universe, right? And if z is very large towards the singularity, alpha tilde also goes to a constant very quickly. This gives you a second Cartesian universe. And this is the value for this function when z is very small or very large. It's very simple, right? It's because it's a tangent function. So you can check the sum of these two components is given by this one. This is just what we found for the Cartesian transition. Okay? And the Cartesian universe is more complicated. In that case, you should consider two coupled equations. Okay? But you can also use a similar idea here to use the constant variant method. You have these complicated equations. This equation, in some sense, can be solved analytically, but not for the explicit form. It's like this kind of computation. Okay. We also have some arctangent. This looks complicated, but you can also know the relation between and after the Cartesian alternation, because thanks to this arctangent, you can show that when z is very, very small, alpha here, alpha tilde, it almost goes to a constant. That means psi is like a logarithmic function. This gives you a very well Cartesian universe. And after the transition, when z goes to very large towards the singularity, alpha also goes to another constant. And you can show that alpha times alpha I is precisely given by this quantity. This we call the Cartesian inversion. And this is the condition when this discussion valid. Okay? And then we can summarize. So when alpha is large, alpha is larger than alpha tc. Alpha tc is here. Okay, we will have we call the transition between the two Cartesian universe, this blue regime. When alpha is smaller than alpha RC is given by this one, in this red region we will have the Cartesian inversion described by the law I just mentioned. Okay, so that means it depends on these two values. We have three different cases. So if alpha tc is larger than alpha RC, so that means in this regime we have the Cartesian transition. In this regime we have the inversion. There is a gap between each other. Okay, and the second case, if these two values are equal to each other, so there is no gap. And the third case, if we have the overlap, okay, between these two behaviors, this I just remind you. So for the Kessler universe, so the scalar is just this form. Okay, that means alpha almost a constant. We can describe it by this very well Kessler geometry. Actually, this case can be explained many previous numerical works. I just list some works. They found some transition between different universes, and this case can explain almost all these behaviors. And for the second one, I can show you one example. So for example, for this kind of theory, okay, this can be have a top-down theory, have a consistent truncation from M theory. This is the form. You can solve this equation numerically. And in this case, because suppose this is the rule that I just mentioned. So if alpha, because this capital D equals 4, okay, we have this rule, and we can fix kappa from here. So this is a rule for the transformation. Okay, that means if alpha is equal to, is larger than 2, so they have this one, this Kessler transition, the sum is equal to 4. And alpha is smaller than 2, we have this one. Okay, this from numerical solution. This is the z psi. Okay, z psi prime. Okay, so you see this is a platform for the Kessler universe. The component is 3.27, it's larger than 2. So according to this rule, it have a Kessler transition, it drops to the new Kessler epoch. So their sum is equals 4, you see, is well satisfied. And then for the second Kessler epoch, its component is 0.7, you see, following this regime, this red regime. So according to this rule, it will have a transfer inversion to another Kessler epoch, and they satisfy this relation. So you see, it goes up. It's 5.49. This is from numerical check. You see, they also satisfy quite well, and you can predict it will not end. It will infinity alternation, and described by this law. Okay, in the third case, we have some overlap. You see, because it's a regime. So both features and both dynamics play important role. And this case has not been explored in the literature before our work. And in this case, since they are too complicated, we are not able to know what happens in these overlapping regimes. Okay, so here is the example. So we consider the 5-dimensional case. This case also can be obtained from superstring theory. This Unicode fix from top-down theory. And you can also solve this solution and see what happens inside the black hole. Okay, so we see in this case, this is the rule. This can be well described or predicted by our analytical law, but in this regime, okay, they are in the overlapping regime. You see there is no well-defined Kessler epoch. And this component cannot be described by the clear law we just proved analytically. So this very complete computation. So this clear law like there. So far, we are not able to understand what happens in this regime analytically. But from numerical, you see there are new features appear. Okay, so far we neglected the contribution from the potential. But what happens if you turn on the potential? Okay. So here you will see the equation motion for the scalar will be modified, some contribution from the potential term. And you can show that alpha prime is like this, have this result. It is negative, okay, inside the black hole. That means if the dV deep psi is negative, since this combination should be negative, if dV deep psi is positive, that means alpha prime should be negative. That means alpha should be decreased, okay? And if this dV deep psi is negative, that means alpha will increase towards the interior. So this is a general feature, independent of the form of the potential, okay? And indeed, we can check this one, like consider some super exponential potential. Okay, like e psi to n. If n is the even power, like 8, n equals 8, you can see this some very interesting oscillation, but this component just decrease. Mention this one. And if we consider some odd power, say is 7, it just, you see, it will increase. And we will have a stable Kessler exponent, because for this is odd power. Okay. And if we consider even more complicated couplings, like this case, you see here we have a platform, this is the Kessler universe. But we found that in this case, this is not a platform anymore. So this is the non-Kessler epochs. That means if we consider some generic couplings, the Kessler universe will be destroyed. So this, in some sense, very surprising result, because in previously people believe that so near the singularity there should be Kessler epochs. But here we show that there can some non-Kessler epochs. Okay, so that means I just want to show you, so inside the black hole, the dynamics is very, very complicated. It can have very rich behavior, far beyond to understand so far. Okay. Okay, I think I should conclude here. Okay, here I show you that we established a no inner horizon theorem for some hairy black holes, for very generic some cases. Okay, and the hairy black hole approach a space-like singularity, is independent of form of the potential that I just showed to you. Okay, and the geometry near the singularity can take a universal Kessler form when the kinetic term dominant. But I just show you some novel behaviors. Okay, that is not described by Kessler form, and even complicated alternation between different Kessler universes. And I just want to convince you the number of horizons inside the black hole can be highly constrained by classical matter. Okay, that's the main result. So maybe there are so many information, but the take-home message is like this. Okay, I want to convince you, so classical matter not only promotes the foundation of event horizon, but they also prevent the appearance of multi-horizon inside the black hole. I think that's the most message I wanted to convince you. Because there are many interesting questions, okay, we can study in the future. So here we consider some simple case, okay, we have some symmetry, okay. So how to consider inhomogeneous case and other forms of matter, okay. And can we generalize our discussion to stationary black hole? So far, we mainly focus on static black hole, have no rotation. So how to generalize our discussion to stationary black hole, okay? And how to understand the dynamics that is different from the Kessler form. So that's also a very interesting question. And can we classify the interior dynamics of black hole? We have made some progress, but they are very complicated behavior beyond our work. Okay? And the more interesting, that's for experimental side or for astrophysics. So is there any quantity we can use to probe the internal structure of black hole? So can we observe some features? Okay. And lastly, what happens if we consider quantum effect? So so far we consider classical theory. What happens for quantum effects? Okay, thank you very much.
Thank you for the wonderful talk. Are there any questions? I have a question. You mentioned the quantum electrodynamics of black holes. How about the quantum thermodynamics of black holes?
You mean quantum QCD?
Yeah.
You mean I just mentioned this one?
Yeah.
Yeah, because it's an open question. We don't know.
Mm.
Yeah, because it will be very interesting because you know the singularity theorem says that near the singularity, the classical description will break down. So quantum effect will become work. So in that case, what happens? In that sense, people believe that we need a quantum gravity theory to understand this feature, right? For quantum effect, if plays a role, like you mean from quantum electrodynamics, quantum chromodynamics maybe will be important here. But so far, I think no one knows what happens. Yeah.
Thank you. Any more questions? If there are no more questions, let's thank the speaker again.
Okay, thank you.